Okay, so it's time to increase the gravity of the situation. We're going to review the universal gravitational equation, write a method for it in Unity, and then check it gives us some interesting results. So here is the Wikipedia page about gravitation. Basically tells us that any two objects with mass are always attracting each other with equal and opposite forces as per Newton's third law. And the size of that force is the universal gravitational constant, which is this tiny thing here, multiplied by the product of the two masses, and then divided by the distance between them squared. Okay, so where are we going to put this in our physics engine? Well, let's dive back over to Unity and take a look. Firstly, I think it should not be a separate component because it's not really optional. Gravity's not optional, right? It always happens. So for now, we're going to put it right inside the core of our physics engine because we can't turn it off. We don't really want to be able to turn it off. We may want to do that later. We'll cross that bridge when we get to it. So what we're going to want is, on the fixed update, we render our trails, and just before we update position, we want to calculate gravity. So let's do some wishful thinking and imagine there's a method called calculate gravity here. Well, of course there isn't yet, but let's write one. Right, so how's this calculate gravity going to work? I'm going to pop it here under my public method. I want to keep my start and fixed update at the top, and then my public methods, and then I'm going to go into my the class methods below that. So here we go. We're going to go calculate gravity. It's going to return nothing. I'm just going to give you the structure for this, and then I'm going to challenge you to do the core of the maths. First, I want to talk about how we're going to find what we're going to be acting on. So what I want to do is I want every physics object to find every other physics object. So how are we going to do that? Well, up at the start, we can say physics engine array. Firstly, let's define ourselves or declare ourselves a physics engine array here. Private variable of type physics engine. And it's a physics engine array like this. Okay, you actually put the array symbol after the type. So private physics engine array called physics engine array. Just be really explicit with the name. Perfect. So we declare it there, and then in the start we go and find all the physics engines. How do we do that? Well, physics engine array. See, this is why long variable names don't matter. Once you've typed them once, then the autocomplete helps you type them again. So please use long variable names. Physics engine array equals game object dot what? Find objects of type is the one we want. Find objects of type, and then let's use the chevron notation, physics engine. And let's remember that it's a method. So great, this physics engine array will find all of the physics engine objects in the game for us. If you want to, you can put a debug statement here, duplicate your ball and check it, but I'm going to leave that till a little bit later. Alright, fine, so that is that bit done. Now, let's just give you the general suggested structure for calculate gravity, and then I'm going to ask you to fill out the core of the code. We're going to say that for each, this reads very nicely, for each physics engine A in physics engine array. So for every physics engine A that we find in the array, go around and do the same thing again, but pull things back that we're going to call physics engine B. We're going to need every pair in every direction. So if there are three things, A acts on B, A acts on C, and then B acts on A, B acts on C, etc. Okay, so physics engine A, physics engine B. Okay, so what the hell's that double loop doing? Well, let's look at it. Before we go any further, let's just debug this out. So debug.log, and let's just say calculating force exerted on, we could even be very explicit and say the gravitational force, and then let's give this thing a name. So let's pick the name off the object, which is physics engine A.name, and then let's just go on to another line. I'm going to indent the start of my string so that this looks very readable. Calculating the gravitational force on physics engine object A, space due to the gravity of, so we don't need gravity twice, and then a space, and then let's put out the name of physics engine object B. Cool, alright, so that log will now tell us what this loop is finding, provided that I close my brackets appropriately. and one more concatenation symbol, and we're good to go. So we're going to loop around all the physics objects. Let's just look at this in context, right? We have a ball. Let's give it a more sensible name. Let's call it ball 1. Okay, and I'm going to duplicate that ball once to start with and make sure that a 2-ball scenario works. We are going to have a little bug. Well done if you've already spotted it. Let's click play. Console, calculating the force on 2 due to 2, 2 due to 1, 1 due to 2, and 1 due to 1. Great, so the two interactions we care about is the force on 2 due to 1 and the force on 1 due to 2. They're the two forces attracting each other. They're the arrows you see over here in Wikipedia, F1 and F2. The minor challenge we have before we go to more than 2 bodies is we have the interactions on themselves. So we need to remove the interactions on themselves. We also need to test that this doesn't fall over when we only have 1 ball. So let's just test with 1 ball. Okay, it calculates the force on itself. That's okay. Let's eliminate this calculating of the force on itself. So we need just one more wrapper, and I won't indent any further than this, I promise you. If physics engine A does not equal physics engine B. So if the two things you found are not the same object, then do this stuff. And then we need one more close bracket. If your indentation is pretty, then you can see that. Otherwise, just do nothing. Right, so let's look at this again. Does it work for 1 ball? Yes, and it calculates no gravitational force. It's great because there's only one object in the world. Let's get a second ball. Let's move it away from the first ball and call it ball 2. And then let's just check. Great, so it calculates 2 forces. Right, okay, so I'm going to empty my fuel from both of my rocket engines here because we don't want rocket fuel and rocket forces coming in. There we go, 2 balls sitting there, no gravity happening yet, but we do have the logs to say that it is ready to calculate the 2 forces. Great, so why don't we challenge you to go ahead and write the rest of the calculate gravity method. So you've got your log statement, what are you going to put in here? That's the question. Have a pop at it. You've got the equation there in Wikipedia. There's no simple operator like star or caret, I'm afraid, in C#, so you're going to have to use mathf.pow and then that distance and 2f for float, so you'll make it taking it to the power of 2, and you'll get a force coming out of that if you set up one of the balls to be at the distance of the radius of the Earth and of the mass of the Earth, then you'll get the force of 9.8 newtons. Otherwise, you'll get whatever force it should be according to the equation. Just check your figures, make sure that's right, and come back to me when you've got that calculating. Okay, cool. So let's take a look at how I'm going to solve this problem. So just going to break it down into bits, really. One of the first things we're going to need is we're going to need this big G thing. So I'm going to put it at the top. Eventually, I think we may end up moving physical constants like big G out even further into something else. But for now, I'm going to have a private constant float, constant because we really don't want it to change. I'm going to copy and paste it from Wikipedia. And then I'm going to fix the problems to minimize the typing that I do. So I just need times 10 to the, well, that's actually a dash 11. I just want E minus 11. And then I want to put in my units. Now, what are the units here? Let's have a little bit of a think about those units. That's how Wikipedia has stated the units. Let's start putting our brackets. So meters, well, hang on, let's be careful. They've had meters over kilograms squared. So what does this actually mean? Let's take what we've got. We've got the units of newtons, which we'll worry about in a minute, times meters squared times kilograms to the minus 2. Fine. Now, we've got the units, the base units of newtons above. Let's take those and put them in the brackets. Then we have kilograms, meters, seconds to the minus 2, meters squared, kilograms to the minus 2. Okay, so there's a lot of different things going on there. What's the end result of this? Well, we have kilograms, meters, and then meters squared, so it's meters cubed. That's grouping all the meters together. Seconds to the minus 2, and then kilograms to the minus 2. Well, that reduces that kilograms to minus 1. And we take it out the front. Now, is that even correct? Let's go over to Wikipedia and have a look and see if they are the right base units, okay? Now, it doesn't tell you here. It tells you, as we said, in terms of newtons, meters, and kilograms, but somewhere else it's going to tell you meters cubed, kilograms to the minus 1, seconds to the minus 2. You see it there at my mouse pointer? M cubed, kilograms to the minus 1, seconds to the minus 2, meters cubes, kilograms to the minus 1, seconds to the minus 2. Okay, well, they've put things around in a different order, but It's good enough for government work. All we need to do is put a float on the end of that and a semicolon, and we have, with a bit of procrastination, set up our big G. Great. Apart from we haven't named it. Big G. There he is. Okay, fantastic. So we have a big G available to us now. Right, so now we need to just go through and pick out all the other things we need. So I'm going to want an r squared, that thing on the bottom of the equation. So I'm going to call it float r squared. It's not a vector, it's just a float here. And this is where, on this line, I'm going to do this horrible mathf.pow. And it's going to be what? Well, it's going to be the distance between them, which we don't have yet, some sort of offset. So I'm just going to say offset, and we'll work that out in a minute. Oops. Now it's determined to mess me up with the autocomplete, but that's fine. We want the magnitude of the offset, if the offset's a vector, and then we want to square it. Fine. Let's get this offset immediately. What is the offset between the two different things, between the two different physics bodies? The offset is simply the physics engine A.transform.position minus the physics engine B.transform.position. That is a vector that describes the difference in position between the two physics engines. What's the type of offset? It's a vector 3. Okay, that's about as long a line as I want. So r squared becomes the magnitude of that offset squared. Then what do we want? Well, we want to work out the actual gravity felt. So vector 3, gravity felt, so where this is the gravity we're receiving, feeling, is gravity magnitude times this offset normalized, i.e. the direction of the offset. Fine. What is the gravity magnitude? This is the main part of the equation you need. It's a float. Gravity. This is where we put the GMM over r squared in. It's big G times physics engine A dot mass times physics engine B dot mass divided by the r squared thing. Therefore, just about on one line, we've got GMM over r squared all on one line, which was what we want to see. Okay, fantastic. Let's try building this. Let's see where we are. A constant requires a value to be provided. Well, if I used an equal sign, then we would have a value. What else have we got to complain about? Looks like nothing. So basically, all of this code is just trying to wrap up so that we can say GMM over r squared on one line, effectively. That's what we're trying to get to. Now, of course, the final thing is we're not using the gravity felt vector, so you need to think a little bit carefully about how we're going to use it. We said that we're calculating the force exerted on A by B. Okay, so which one is feeling the force? It's physics engine A is feeling the force, so we add a force to its force list. And what is it? Well, it's in the opposite direction of the vector. So of the offset vector between the two of them. You could just get it round the wrong way and realize you have to reverse it, but I'm going to save you the trouble. So it's minus gravity felt vector. Okay, with a minus sign, you can reason it, and it's good to know where you are, but sometimes you want to just do it, and when you're aware that it's either plus or minus, just run it and check and see. So if we have two bodies here, before we click play, what are we expecting to see? Well, I'm expecting to see rocket trails coming away from the top ball and away from the bottom ball, so both away from the center, as if there were rocket trails pushing the balls together. Let's try. Oh, exciting. That's what's happening. So that's it. We have rocket trail vectors. They're quite long. They're quite surprisingly long. How big are the masses? They are large masses, though. These things have 2 million kilos each. But interestingly, because they're 2 million kilos each, they also have a massive inertia, which an inertia is a resistance to acceleration, so they're not moving very fast. They are slowly picking up velocity, but there's only 30 newtons, about 3 kilograms here on Earth of force, on something of 2 million kilograms, 2,000 metric tons, so they're not accelerating very fast. Let's add a few orders of magnitude to the mass here. I think you need to get 4 orders of magnitude, and suddenly, because one of them is massive, boom, and then the calculation will break down when they try and pass through each other. Awesome! We now have universal gravitation being modelled. Now, just for a bit of fun, you've earned it. Why don't we just stick a third ball into the equation and move it somewhere else altogether? And they're always going to be in a plane, by the way, with 3, of course. You can always define a plane between 3 points, so don't worry too much about where they are. Just stick 3 of them in. If you want to highlight all of them and turn their mass up about 4 or 5 orders of magnitude, then just sit back and watch what happens. And in some situations, you'll end up with nice, kind of stable, weird orbiting behavior. In other situations, it'll do something like just ping off into the distance. So it's fun to watch. If you get the arrangements of your masses right, as it were, you'll end up with stable orbits and weird things that evolve over time. And it can be quite enticing to watch. So enjoy playing with that. And now you have n-body gravitation working. One hell of a step up on what Unity does by default. So congratulations on that, and I will see you soon.